welcome to another module in this massive open online course. So, we are looking at pulse amplitude modulation, correct, where the amplitude of a series of pulses is modulated using the sample values of the sampled signal, correct. So, we are looking at pulse amplitude modulation. We are looking at pulse amplitude modulation, correct, okay, where we have said that we have our original signal m of t. It can be represented as the modulus sample it with the impulse, that is your impulse sampling signal, impulse sampled signal, which is summation n equal to minus infinity to infinity m of nts delta t minus nts. This is our original impulse sampled signal, correct. This is our impulse sample signal. And what we want to do now is our pulse amplitude modulated signal. Remember, that is our MPT. This is basically, if you look at this, this is your n equal to minus infinity to infinity mnts h of t minus nts, where, so this is my pulse amplitude modulated signal. So, this is our pulse amplitude modulated signal, which basically is this corresponds. So, my impulse is basically h of t, that is my impulse. Remember, it is, or I mean, it is my pulse. My pulse is basically of width 0 to t. This is my pulse of height 1, correct. So, this is my pulse, and what we are doing is basically we are shifting the pulse to every ts and scaling, or basically modulating it by mnts, which is the value of the sample at the nth sampling instant, that is nts. Okay. So, this is basically shifting pulse nts and scaling by m of nts. Hence, I can also represent this as, and therefore, we have said that we can equivalently represent this pulse amplitude modulated signal as, if you remember, this is your impulse sampled signal, that is mnts n equal to minus infinity to infinity delta t minus nts. This is your m delta t convolved with h of t, and that gives me basically your pulse amplitude modulated signal. Okay. That is mnts impulse convolved, impulse shifted impulse t minus nts convolved with ht gives h of t minus nts. Okay. So, this is your pulse amplitude modulated signal. Now, the interesting thing about this is basically, if you look at this, this is basically m delta t, your pulse amplitude modulated signal MPT equals m delta t convolved with h of t, which means if I take the Fourier transform. Now, if I look at the Fourier transform of this pulse amplitude modulated signal, which is denoted by MP of f, Naturally, in the Fourier frequency domain, convolution in the time domain becomes multiplication in the frequency domain. Therefore, MP of f is given, would be given as MP of f would be your Fourier transform of the impulse sample signal times h of f. So, m delta f equals Fourier transform m delta t, and hf equals Fourier transform I am denoting this by pt, not ht. So, this will be your pt. So, the pulse shape is pt. So, this will again be here, it will be pt. So, pt minus ts. So, this is pt convolved with pt. So, this will be pf, where pf is a Fourier transform of the pulse shape pt. Pf equal to Fourier transform of the pulse pt. Okay. So, that is what we have, that is the Fourier transform of the pulse pt, correct, where we are using pt to denote the pulse shape. Now, we already know the Fourier transform of m delta t. We know that the Fourier transform m delta t, which has Fourier transform m delta f, well, that is simply your sum of shifted replicas of the original spectrum m of f, correct. So, this is m of f. So, this is 0, this is fs, this is minus ff, this is your m of f, this is your m of f minus fs, and so on. This is your m of f plus fs, and so on, m of f plus fs. And therefore, the condition for aliasing, that is condition for avoiding aliasing or condition for avoiding distortion, remains the same, all right. So, we are taking the spectrum m delta f and multiplying it by hf. So, that does not cause overlapping of the signal copies, correct. So, the condition for avoiding aliasing still remains the same. So, condition for avoiding remains same, that is no aliasing if fs greater than equal to 2, no aliasing if fs is greater than or equal to. So, this is your fm, which is the maximum frequency of the signal, okay, where the sampling frequency fs, remember fs is the sampling frequency, equals 1 over your ts, fm equals maximum frequency of signal, or basically also the bandwidth of the signal. Now, we need to find Pf. Pf is the Fourier transform. So, we need to find Pf. Pf is the Fourier transform of the pulse filter Pt. Okay. So, we need to find Pf, which is basically Fourier transform. Remember, Pf which is basically Fourier transform of Pt. We need to find this. And remember, Pt is basically, if you look at this, Pt is basically this pulse of height 1, this is Pt. Now realize this can be obtained from this pulse, it is a shifted version of this pulse of height 1 spread from, so this can be obtained from this pulse or this can be obtained from this pulse, which is basically your pulse from minus t by 2 to t by 2 of height 1. If I shift this by t, if I shift this by rather t by 2, correct, if I shift this by t by 2 or delay by t by 2, rather I should say delay by t by 2. So, what we have is the pulse of unit amplitude between minus t by 2 to t by 2. If I delay this by t by 2, then it will become, then it becomes Pt, which is the pulse of unit amplitude, unit height between 0 and t. Alright. And I already know the Fourier transform of this, the Fourier transform of the pulse with unit height between minus t by 2 to t by 2. This is basically my t sinc ft. This is basically this pulse, if you remember, this is basically my Pt by 2 of t, that is where Pt by 2 of t is 1 if mod t less than or equal to t by 2 and 0 otherwise. So, this is Pt by 2 t delayed by t by 2. So, therefore, Fourier transform of this using the modulating property, that is x t minus t naught, Fourier transform will be, if Fourier transform of x t is x f, this will be x f e to the power of minus j 2 pi f t naught. Therefore, t sinc, we have Pt, our pulse Pt equals basically your Pt by 2 delayed by t by 2. Therefore, this will be Pf, the Fourier transform of this pulse will be, well, it is going to be t sinc ft e to the power of minus j 2 pi f t naught, which is equal to t by 2, which is e to the power of minus j pi f t. So, the Fourier transform or the spectrum of the pulse is t sinc f t e to the power of minus j pi t. This is your spectrum of pulse. And interestingly, if you look at the amplitude spectrum, e to the power of minus j pi f t is simply a phase factor. So, therefore, amplitude spectrum is still the same, that is magnitude t sinc f t, and the zeros of this in the frequency domain, zeros in frequency domain are at k by t, that is integer multiples of 1 over t, where k is any integer, but k not equal to 0. Of course, at k equal to 0, this is equal to t. So, if you look at the magnet, so the magnitude spectrum of P of f, the pulse filter, is again magnitude T sync Ft in the frequency domain with zeros at 1 over T. Now remember, T, this duration of the pulse is much less than Ts, therefore 1 over T is much less than 1 over T is much greater than 1 over Ts or Fs. Okay. So if you plot this, now if you look at this, this is going to look something like this. So we have, let us plot this. So we have our m delta f, which looks something like this. Let us say it is not aliased, it looks something like this. So this is your m delta f, this is your Fs, which is 1 over Ts, this is your Fs 1 over 2 Ts. Okay. And now we have T much less than Ts, which implies 1 over T, that is 1 over T is much greater than 1 over Ts, and therefore the pulse filter, the first zero of the pulse filter will lie much beyond 1 over Ts. So it will be something like, so this is my minus Ts and this is my 1 over Ts. So the zeros will lie something over, so it looks something like this, your sync filter will look. So this is your P of f, correct. This is your P of f, which is magnitude T sync Ft. Of course, at 0 this value is T, and the zeros, or first 0, let us put it that way, first 0 lies much farther than. So if you look at the first 0 is at 1 over T, first 0 on the positive axis is at 1 over T. At 1 over T on the positive axis, and then of course on the negative axis first 0 is at minus 1 over T. And now what we have is this whole m delta f, that is the impulse sample signal, is multiplied, spectrum m delta f of the impulse sample signal is multiplied by P of f, which is the spectrum of the pulse shaping filter. Therefore, what you are going to have is the net spectrum of MPF will be, you will again have several copies, which will be multiplied by the sync pulse shaping filter. So this will be, so if let us say this is Fm, this is let us say minus Fm to Fm, this is your m of f times the magnitude spectrum. Let us say we are plotting simply the magnitude spectrum, magnitude m of f, T sync f t, okay, and this will be from Fs minus Fm to Fs plus Fm. This will be something like this, and this will be something like, the amplitude, the maximum amplitude is decreasing because of the sync, because of the windowing by the sync. So, you can see the maximum amplitude is decreasing progressively as you go to the right, which was not the case in the impulse response frequency of the impulse sample maximum. So, first of all it is distorted, and maximum amplitude or peak amplitude, peak amplitude in the frequency domain is decreasing, peak amplitude of each copy is decreasing with frequency because of windowing by the sync, correct. Because of windowing by the T sync Ft. And therefore, now Reconstruction is again simple. This is your basically this is your m p of f, which is equal to, remember, m delta of f times the pulse shaping filter p of f. This is the Fourier transform m p of f, or basically Fourier transform of pulse amplitude modulated signal. Let us write that also, Fourier transform of your PAM signal. Now, obviously, to reconstruct the original signal, we have to isolate the baseband component, or the component around the zero frequency, right, the copy of the spectrum around zero frequency. But now we also have to invert the distortion. So, we have to also invert the distortion caused by the windowing by the sink. So, first for reconstruction, so let us now talk about reconstruction if there is no aliasing. Alright, obviously the condition for aliasing still is there. So, signal reconstruction in absence of aliasing. Which means absence of aliasing means, naturally it means that your Fs is greater than or equal to twice Fm. Now, in that scenario, first what we do is we low pass as usual, low pass filter with cutoff as your Fs by 2 and 1 over T, which will basically, and low pass filter with so first low pass filter, and this is basically your 1 over this has to be, so you have to adjust for the scaling which has to be that scaling is basically Fs is multiplied by Fs. So, 1 over Fs, or basically you have to multiply this by this has to be multiplied by Ts. So, you have to multiply by Ts, and by the way the expression for this is basically your m delta f into Pf. Now, m delta f, remember we have m delta f equals, we know the expression for this. So, let us write it at the appropriate place. We know the expression for this, well we know the expression for m delta f. So, we know the expression for m delta f, this is equal to summation, or let us just write it down. We know the expression for m delta f equals, that is the response of the impulse sample signal, that is summation n equal to minus infinity to infinity Fs m f minus n Fs. Pf we know that is basically T sinc f t e to the power of minus j pi f t, and therefore, m p of f, that is the response of the pulse amplitude modulated signal, that is m delta f times p f, which is basically your summation n equal to minus infinity to infinity, n equal to minus infinity to infinity Fs m f minus n Fs times e to the power of minus j pi f t. Okay, times e to the power of minus j pi f t. Okay. This is the response. Now, to reconstruct it, first low pass filter with cutoff again Fs by 2, that is a first step. This is your first step. Now, in step 2 you also have to cause the invert the distortion of this amplitude spectrum of the copy around 0 frequency, which is caused by windowing with the sinc function. So, in step 2 you have to, in that frequency band, step 2 reverse basically distortion caused by windowing with the sinc function. So, basically you have to multiply by the response in Fs by 2 to Fs by 2, which is 1 over Pf, correct. So, that will be the inverse of the sinc, which will be something like this, correct, something like this, that is 1 over your Pf in, but this is necessary to be done only in your Fs by 2 to Fs by 2 minus Fs by 2. So, it is necessary to do this only in Fs by 2 to minus Fs by 2, correct. So, this is your 1 over Pf in minus Fs by 2 less than or equal to F less than or equal to Fs by 2 and 0 otherwise, because we do not care about the reconstruction in the outside band, alright. We only want to reconstruct the center band or the component around the. So, this is your reconstruction filter. If you call this H of F, this is basically your reconstruction filter, or we can call it the equalizer. And the reason for this is as follows. Let me just write it and explain this. This is also known as an equalizer. The reason for this is that because the original sinc windowing is multiplying by the sinc, alright, which has basically a decreasing amplitude. Now, what you are doing, you are trying to invert that so as to make the net response, that is the multiplication of this filter with the sinc to be unity, alright. So, that way you are distorting. So, whatever distortion is caused by the sinc windowing, you are reversing that by inverting that. So, the net response, if you look at it, will be flat, that is you are equalizing it across the frequency domain. So, this is also known as a equalizer, alright. So, first you pass it through low pass filter similar to reconstruction from the ideal impulse sample signal, followed by an equalizer to invert this distortion caused by windowing due to the sinc function between minus Fs by 2 to Fs by 2. Therefore, the reconstruction will be as follows. The reconstruction will be, and then once you do that, what you will have is, you will have your original message spectrum, which is, well, minus Fm to Fm, this is your m of f. So, therefore, the reconstruction procedure would be, I have my PAM signal or my MPT, I pass this through first LPF, cutoff is Fs by 2, okay. This is my PAM signal. Follow this by equalizer, that is 1 over Pf, and then you get back MT, which is the original message signal, of course noting that if there is no aliasing. This is your original message signal, this is the original message signal. Okay. So, you get back, so you pass, this is the, take the PAM signal, you have your low pass filter, that is low pass filter between minus Fs by 2 to Fs by 2, okay, that is the pass band of this low pass filter, that is pass band until Fs by 2, cutoff frequency at Fs by 2, okay, and then you pass it through an equalizer. What the equalizer is doing is simply it is inverting the distortion caused by the sync windowing function, the frequency domain, and then you get back the original signal MT. Alright. So, basically the pulse amplitude modulated signal has to go through a two-step reconstruction process. First low pass filtering to extract the component at 0 filtering, and of course subsequently the equalizer. And of course, you can combine both these things into a single filter, that is the low pass filter itself. If you design the low pass filter response such that it is 1 over PF in that frequency band, then naturally you can reconstruct. Alright. So, but it is easier to think of it in terms of first low pass filtering operation followed by an equalizer operation, although both there can be a combined filter. So, these can be put together because both these things are linear operations. These can be, we can also note that these can be combined into a single filter. Alright, and then one can reconstruct the original signal MT from the pulse amplitude modulated signal MP of t. Alright. So, we will stop here and we will look at other aspects in the subsequent modules. Thank you.